Hello, welcome to Physics 2, Lecture 25.3, Induced Current in a Circuit. So, in our previous discussion, we talked about a conductor that was moving through a magnetic field, and that caused a separation of charge, and that gave us a potential difference in an electric field inside the conductor. Well, that's great and all, but it's not super practical because even though the charges are separating, they don't have anywhere to go. And so as a result, you're not establishing any current, so there's no real use of this. However, if you were to take that same rectangular conductor we talked about in the past and include it in a circuit, well then current can be sustained. Now, when I say include it in a circuit, what I mean is something like this. If you take that conductor, or the wire, which is this gray rectangle here, and you add it into a U-shaped rail, which you see in yellow in the background, you have a complete circuit now. So as this conductor moves through the magnetic field, we can get some current to flow in a path now. So let's take a closer look at this and then mathematically start to describe a lot of what's going on in the background. So, looking at the same image, the charges that are separating in the conductor due to the motion of the conductor in the magnetic field, remember we saw that the positive charges get pushed to the top, negative charges are left at the bottom. Well, as the positive charges are being pushed upward, they now have a free path to flow around as current. And so you're getting a current flowing, in this case, in a counterclockwise direction through this portion of the circuit. Now this acts exactly like a battery in the sense that it is driving current in a circuit, which is why in our last lecture we talked about a difference between a battery, which is a chemical EMF, electromotive force, and this, which is a motional EMF. They both do the same thing, they both establish a potential difference between the two ends, and thus drive current in a circuit. So again, you can kind of think of this as a battery in that it produces a current. Now that current can be given by Ohm's law, which was delta V over R, or in this case, epsilon, or EMF, over R. From our previous lecture, we saw that the EMF was given by VLB, so we just plug that in here for our expression of current. So current can be given by VLB over R, which is still just Ohm's law. And note again that V is the speed of the conductor, L is the length of the conductor, B is the strength of the magnetic field, and R happens to be the wire's resistance. So, we have one more technicality to go through. We're assuming, up to this point, if we look back at that image, that we are moving this conductor with a constant speed V. But that's not possible on its own. In order to keep it moving at a constant speed v, there has to be some sort of a pulling force, whether it be a hand physically pulling the wire to the side or something else. We need to pull it with some force. Now, the question might be, why would that be the case? Why can't it just move with some constant speed v? Well, keep in mind there's magnetic forces going on here. In this situation, if you look at the diagram, we have a current moving upward and a magnetic field pointing into the screen. So use your right hand rule. If your thumb points upward with the current, your index finger points into the screen with the magnetic field, well then your middle finger will point to the left, indicating that there is a magnetic force acting on this wire to the left. In other words, in the opposite direction that it's moving. So you have this force here resisting its motion. So as a result, this wire will try to slow down on its own and come to a stop. So to overcome that, you need to have a pulling force to help assist its motion to the right. Now, this force must balance the magnetic force, so we can set those two forces equal to one another. In other words, we set our pulling force equal to the magnetic force on a wire. If you recall from a couple discussions ago, the magnetic force on a wire is given by ILB. This looks a little crazy because I'm doing a derivation here, but it's ILB. And remember on our last slide, we expressed the current as VLB over R. Okay, so this is just the force on a wire that we talked about before, and then we plugged in our expression for current. Now I simplify this. We have two L's and two B's, so we can simplify by simply squaring those two terms. So we end up with the force is being V L squared B squared over R. Now, we can also look at this in terms of energy. If we're talking about pulling this wire to the right, well, realize that means you're doing work on the system. And if you're doing work on the system, that means power is being input into this system. And so we can come up with an expression for the power generated by such a device simply by using an expression that comes from Physics 1. Power is equal to the force times the velocity. So, if we take power equals force times velocity, all we're doing is taking our equation here from our last slide, force, and multiplying it by V. So, our inputting power is force times V, so we end up with V squared L squared B squared over R. So this is the power that is input into the system because you are doing work by pulling this wire to the side. But furthermore, power is also dissipated or removed from the system because there's a resistance in the rail in the wire. And so we can also find an expression for the power that is dissipated in the circuit. In this case, we can use an expression from earlier in our course, power is equal to the current squared times the resistance. If we do that, believe it or not, we end up with the exact same equation, V squared L squared B squared over R. Now, if you're wondering where this came from, again, we came up with an expression for current 2 or 3 slides ago. So we squared that term and multiplied it by R. So we have an interesting result. The power input into the system, oops, this isn't supposed to say input. This is supposed to say dissipated. That's my bad. I copy-pasted that and forgot to change it to dissipated. Anyway, so the power input is exactly the same as the power dissipated. Well, this should actually make sense. The rate at which you're doing work is balanced by the rate at which the energy is being dissipated. This is simply the conservation of energy, taking a physical manifestation, well, I guess not physical, a mathematical manifestation in our work here. So the power input into the system equals the power dissipated, and that's simply the statement of conservation of energy applied to this situation. Okay, so before we conclude, let's kind of do what we have been doing lately, where we go over one kind of interesting example, and then we'll do a quick check question to conclude. Now, anytime we have a device that's taking mechanical energy, so actual motion, and turning it into electrical energy is what we call a generator. So what we just looked at here is a generator of sorts. It's a very, very simple one and not the most practical generator possible, but it does generate power or energy. And so this segues us back to our discussion on generators. I did bring this up in a previous lecture briefly, but we've learned quite a bit since then, so we're going to take this a little bit further. This first paragraph I have here in this image should look familiar. This is all relevant to what I discussed before. But in many generators, you have a coil that rotates around in a magnetic field. So that's what you're seeing here on the sides. You have magnets with a north and south, so a magnetic field is pointing from left to right in this case. Because of that, as the coil rotates, the left edge is always moving up through the field, the right edge is always moving downward in the field, and so as a result, you are inducing a current in that coil. So you can see that here, it's giving us a current moving through the coil. So here comes the part where we take it a step further. We didn't talk about what happens to that current once it's produced in this coil. So once it goes through the coil, it comes to these slip rings, and these brushes take the current off. In other words, the charges are transferred externally into some additional circuit. Well, as that happens, as this thing is rotating, we get a sinusoidal wave in potential, or EMF. In other words, it's increasing, then decreasing, then increasing, decreasing, and it goes from positive to negative back and forth as this thing rotates around and around. Power plants specifically use these types of generators to give us electricity in our houses that have a varying voltage. You might have heard me use this term before, AC current or alternating current. It comes about because of this exact reason. We have an alternating potential difference, and it happens to change like 60 times a second in a standard household outlet. And so it's alternating, and so we call it AC or alternating current. So this is just giving you a little bit of a hint of what's going on in the background of everything in everyday life. It's beyond the scope of our particular class, but you can talk so much more about alternating current. This is the closest we will come to actually discussing it, though. So, with this, let's go ahead and do one quick check to close out the lecture. So you have an image on the right, and it says an induced current flows clockwise as the metal bar is pushed to the right. What direction does the magnetic field point? All right, well, it's a right-hand rule application, and you should find that it points into the screen. How do we know this? Well, we know the conductor is moving to the right, so our thumb points to the right. We know charges are forced upward through the wire, so our middle finger points upward. So if our thumb is pointing to the right and our middle finger is pointing upward, that means our index finger has to be pointing into the screen. And I wish there was an easy way for me to show you my hand gestures that I'm making at the time, but try to follow along with your right hand rule, and you should get into the screen as your answer. All right, so that concludes this lecture. Thanks for watching, and have a great day.